Hi folks, we're taking a look at exponential and logarithmic differentiation. So exponentials with a base of e are easy to differentiate. E to the x differentiates to e to the x. As always, the chain rule can apply, so if you have e to the 3x, that means there's some sort of like inner function happening. E to the 3x is right there. When you differentiate, the first thing you do is nothing, just rewrite e to the 3x. And then you have to take the derivative of the inner, which would just be 3. So in the end, we get 3 e to the 3x. And that's summed up in this rule over here. But that's really just the e to the x goes to e to the x, and take into account the chain rule. We can use other bases as well, but notice if you have a to the x, where a is not going to be e, then you have to throw in an extra tax here of ln a. So if we have 5 to the x, still becomes 5 to the x, and pay your tax of ln 5. Chain rule still applies, so 5 to the 3x, that's got an inner part of 3x. So when we differentiate, pay our tax for having a base of 5. Then we have nothing happens, just stays the same. And finally, from the chain rule, we have the derivative of 3x. You can put that all together in a different order if you want, and call it 3 ln 5 times 5 to the 3x. But either order is fine. Differentiating natural logs is pretty easy too. Ln x turns into 1 over x. Now the chain rule still applies, so if you have ln of f of x, it turns into 1 over f of x times the derivative of the inner, which would be f prime. Or you could just write that as f prime over f, or if you want to sum it up in a catchy little song, it's original on the bottom, derivative on the top. So here's the original on the bottom, here's the derivative on the top. Let's try one. We've got ln of 3x squared plus cos x. So the original we're talking about here in original on the bottom would be this 3x squared plus cos x. And its derivative would go on the top. So the derivative of 3x squared plus cos x would be 6x minus sine x, which we're showing right here. And then we're done. It's pretty straightforward. You can use other bases. So we can have a log base 4, but you need to pay a tax, just like you did with the exponentials. This time, the tax shows up on the bottom of this fraction. But it's still basically original on the bottom, derivative on the top. So if I have log base 4 of 3x minus 1, here's our tax for using a base of 4. We have to put ln 4 on the bottom. And then it's original on the bottom, there's my 3x minus 1, and its derivative on the top. Now this song is good for differentiating logarithmic functions. It's super catchy, but don't start using it for everything, like polynomials or something. It's just for logarithmic functions. Log laws can make our life easier when we're differentiating logarithmic functions. Typically, we want to use them before differentiating. So here are our 3 log laws from Math 621b. You can take an exponent down front. If you have the log of a product, then you can split it into the sum of 2 logs. And if you have the log of a quotient or division, then you can split it into the difference of 2 logs. So when I look at the example question here, it's ln of a huge mess. I could try and sing my way through it and put that on the bottom, but then finding its derivative to put on the top is going to be extremely difficult. So instead I'm going to ask myself, what log laws can I use? And the one that really jumps out to me first is that there's division here. It looks like this log law, the third one that's written here. So I'm going to split it into ln of x to the 5 cos x minus ln of the square root of 3x minus 1. There I use that first log law. And then what I might notice is that there's a product right here. Okay, so that means I can use that log law. So I can split it apart into ln of x to the 5 plus ln of cos x. and I still had that ln of 3x minus 1. It was square rooted, so I'm going to call it a power of a half. And lastly, what I can do is I can use this power law. So all these powers can come down front. That x to the 5 now becomes 5 ln x. That ln of 3x minus 1 to the half becomes a half ln 3x minus 1. Notice that this is all still saying y equals. We're just using log laws. Yes, we're pulling down powers, but it's not through differentiation. Now we can finally differentiate. And how we're going to do it? We're going to do it by singing. So 5 stays because it's a coefficient. Ln x turns into 1 over x. For ln of cos x, I'll go original on the bottom, and the derivative of cos x is negative sine x. Derivative on the top, right there. Minus negative a half, so half's going to stay, and then original on the bottom because it was ln of 3x minus 1, and its derivative on the top. And then after that, we can just go ahead and collect stuff up. So we have 5 over x minus sine over cosine, so that's just tan x. And in the last one, we'd have a 3 on top, and then 2 by 3x minus 1 on the bottom. Now that might look like a lot of work, but if you do it without the log laws, it is going to be a million times more painful than that. The last thing worth mentioning here is that there are restrictions in the domain of log functions. So you can only take the log of a positive value. If I have a function like this one, ln of 3x minus 1, I can't put 0 into that function. That would cause me to take the logarithm of negative 1, which is not okay. So the domain of that function comes from the inequality 3x minus 1 has to be positive, or 3x minus 1 is greater than 0. That means 3x is greater than 1, or x is greater than the third. There's the domain of the original. Now we can differentiate this function. Let's see what we get. We get original on the bottom, right there. Derivative on the top, right there. Okay? And it looks like you can put in 0 into that function, but that would be really weird. That would mean that we're finding the slope where the original function doesn't even exist. That's bizarre. So any restrictions that are on the domain of the original need to carry through for its derivative. Often we don't bother to write the domain of the derivative, but it is true that those restrictions follow us through. So here's a list of all the derivatives that we dealt with in section 4.4. For my money, I'd be remembering this one. E to the x goes to e to the x. The one below it is just the chain rule applied to that. I'd be remembering this one, and how I'd remember it is just to say, listen, if I have a base other than e, I need to pay an extra tax of ln of that base. I would remember this one, original on the bottom, derivative on the top, and that includes the chain rule in it already. And I would remember one of the last two, just to make the point that you need to pay a tax if you've got a weird base, a base other than e. So I would sing my way through all the logarithmic differentiation, and I would look for opportunities to use log laws before differentiating. I hope this has been helpful, and good luck on the formative quiz.